Good morning there, Unit 3 and 4 General Math Goers. Taz here. I'm making this video because unfortunately I had to stay home as Rio is feeling a little bit crook and will be going to daycare. So in preparation for this, I'm going to be making videos for example 22 for exercise 7D, which you can see on the screen, and then also showcasing how to go about 7E. So to give you a snapshot, we started 7D, the notes for this yesterday, and the intention was to give you this as homework, but unfortunately we ran out of time for example 22. So example 22, if you haven't done so yet already, you can go ahead and print off the notes for example, or for all of 7D rather, and with those notes stick them into your exercise book. And in example 22 looks into reducing balance depreciation with recurrence relations. So here we have a recurrence relation that can be used to model the value of office furniture that has a purchase price of $9,600, and this depreciates at a reducing balance rate of 7% per annum. This then implies that to get your next result or next number, you take the previous one and you multiply this by a number that's lower than 1. Because it's reducing and it's at a 7% rate reduction, this will be a 0.93 multiplicative factor. So to work this out, you just do 7 over 100 and you minus this from 1. So in this recurrence relation, V of n is the value of the office furniture after n years. We're dealing with n amount of years being the time frame. So we're going to use this recurrence relation to find the values of the office furniture to the nearest cent after 1, 2, and 3 years. So all we do to get this is, if we know what our initial amount is, multiply this by 0.93 each time to get a new result, and then that result gets multiplied by 0.93. And this happens again and again and again until you get V of 1, V of 2, and V of 3. And this is correct to the nearest cent, so 2 decimal places. Second question, if the office furniture was initially purchased in 2023, at the end of which year will the value of the furniture be less than $7,000? You would just go ahead and keep doing this approach until you get to an amount that's less than $7,000. Then you just count out how many times this operation has been applied. So not including the first line, because that's our initial amount, 1, 2, 3, 4, 5. So the value of the furniture first drops below $7,000 after 5 years. And because it's asking the specific year of when this will be, it says 5 years attached to 2023. That's how you go ahead and tackle the example for 7D, example 22. I'm going to go ahead now and look into exercise 7E. Now again, 7E has been put up on Google Classroom, and you can go ahead, print this off, stick them into your exercise book, and you're going to use this video to help you tackle the example questions, and then you're going to go ahead and answer the set designated questions left by me. So the learning intentions for this particular exercise is to be able to write explicit rules for geometric growth and decay, use the explicit rule to find the value of an investment or some other type of condition after a time frame, in this case n years. We're going to calculate the value and total depreciation of a particular asset after a period of reducing balance depreciation, and to be able to use TI-inspired calculators to solve geometric growth and decay problems. So now we're going to delve into the world of geometric growth and decay with a particular multiplicative factor. And you're going to see these two different letters thrown around, small r and big R, and it's really good to know and be aware of the difference of what these intend, what they mean, when to use them and how to use them. So taking a step back, we want to make sure that our recurrence relation for arithmetic and writing a rule from a recurrence relation is down pat. So remembering that recurrence relation occurs, say for instance, I had an initial condition v of 0 is equal to, say, 30. This could be an investment of some sort, or like a starting value of pocket money. And to get my next result, vn plus 1, I take my previous v of n, and then I just add 3 each time. Now this is the recurrence relation format of this, but then there's this process where we want to write a rule. I want to know how to write this so I can be able to tell you how much money is in an account after 70 iterations. Let's say n in this case is days, so after 70 days, and I don't want to rely on the previous 69, 68, 67, etc. to be able to get this. So we write a rule. Our rule always starts off with writing v of n is equal to, we always tell the assessor where our initial amount is coming from. It starts off at 30. Because this is going up, we are adding, and whatever this rate is, 3 times n. So you can see this familiarity with the numbers that are being used. It's just written in a different position. This can also work obviously for arithmetic subtraction, or decay, or depreciation. Maybe I have a v of 0 is equal to 12, and to get my next term, I will get my previous term and subtract 13 random numbers. Obviously we'll get into the negative numbers of some sort, but I don't really care about that. I care about that transition to a rule. So a rule always starts with v of n. Tell me what my initial amount is. Tell me how much I'm going up or down by. In this case, it's going down. So yeah, obviously we can use this rule to determine a particular n value, maybe n of 30 or n of 50 for both of them. You would just go ahead and do a straightforward substitution. So what this exercise 7e looks into is taking the same concept of a recurrence relation and running a rule from it. But this time it's going to be dealing with geometric growth and decay. So we're dealing with values where there is multiplication that's happening. So if the recurrence relation for geometric growth or decay looks like this, I have a starting value of some sort, and to get my next value, I multiply my previous value by a particular multiplicative factor, say big R, and there's a reason why I say these fancy words. If I want to write this in rule format, same thing applies. V of n, always starts with a v of n, is equal to, and we take what our multiplicative factor is, what is being multiplied by, raise this to a power, and multiply this by the initial amount v of 0. Now you can also write this in the different position. If you end up writing v of n is equal to v of 0 times r of n, that is completely fine. In fact, you won't necessarily lose any marks of any sort because it's communicative. You can flip them around. So it is in your best interest though to write it in this template, because that just seems to be the template that seems to be accepted. So what we're going to do is we're going to write the rule for these two recurrence relations that are geometric, and then we're going to use this rule to find the value of v of 6. So for the first one, A, our rule, and this is what you're going to copy down now under your space, assuming you've printed this out. Our rule will start off with v of n is equal to, now we need to know what the multiplicative factor big R is. This here is 4, so we're going to write 4 to the power of n, and we're going to multiply this by whatever our initial amount is, 5. And there we have our rule. So similar to the process, you can see this familiarity of numbers. It's just written in a different way. B, our rule is V of n is equal to what our multiplicative factor, 0.5. And again, this doesn't have to be greater than 1, it can be less than 1 as well, to the power of n. And this is multiplied by the initial amount, in this case 10. So now that we've got these values, we are going to try to work out what V of 6 is. So V of 6 of the first one, this is just a straightforward substitution. So it's 4 to the power of 6 times our initial amount is 5. If done so correctly, you should get 20,480. And again, V of 6 for the second one, 0.5 to the power of 6 times 10. Now pause. We are dealing with a number that's lower than 1, so we're expecting a number lower than 10. Because our multiplicative factor is lower than 1, it's not greater than 1, it is decaying. It's halving it. It's halving it again and again and again, and it's doing this 6 times. In this case, we're going to get a 0.15625. So we're looking to try that again. We're going to look into compound interest loans and investments, so seeing what we can do with this big R. And in real life situations, when things grow and it's in, say, compound format, it is going to be increasing by a certain percentage. If this is the case, this is going to be a multiplicative factor of 1 point something. So say for instance something were to increase by 17%, your multiplicative factor will be 1.17. Now there is a format of trying to work out what this is. In other words, if I have a multiplicative factor of big R, this means that it is equal to this. So we're replacing big R now, which we saw in the previous one here, with a specific way of writing this if there's a percentage increase or decrease. This is equal to 1 plus small r over 100, and where small r would just be a particular percentage rate that the question gives you. Now this again happens with reducing balance depreciation. The only difference is that we are dealing with minus, because it is losing a certain amount as time goes on. So your multiplicative factor will be a value that is less than 1. If it's greater than 1, so 1 point something, it's increasing. If it's exactly 1, it stays the same. If it's decreasing, it will be 0 point something. And there again, in this case, your R is going to be equal to 1 minus a small r over 100, where again, R is a percentage rate that's given to you within the question. I will stop here. This will be part 1. Part 2 will be found in the next video.